centuries, humans have been looking up, observing the sky. As they did so on a daily basis, patterns emerged. Stories were formulated, and time was quantified. Our ancestors looked at the sky not only in admiration of its beauty, but as their timepiece and terrestrial guide. They saw the sky as their compass, calendar, and clock. The most obvious pattern presented to ancient observers was the behavior of the sun.
It's easy to notice, day after day after day, the sun tends to pass across the same area of the sky. This was called the south, from the Germanic phrase, the region of the sun. From the Germanic words for dawn and evening, east and west also began being used. This was the start of a directional system. This consistent solar path across the sky is due to the Earth's rotation.
Since the Earth rotates counterclockwise as seen from above the North Pole, the sun will always appear to rise over the eastern horizon. As the Earth continues its rotation, the sun will lift and slide to the south. At 12 noon, the sun is directly south. From this point, the sun will descend and carry westward as the Earth continues to rotate. The sun finally appears to slip under the horizon, to the west. After the sun sets, it is possible to detect the rotation of the Earth by watching the nighttime stars. Through the night, the stars will copy the pattern of the sun as they rise from the east, drift across the south, and set in the west. This will continue until the Earth is rotated enough to bring the sun above the horizon to begin another day.
If it is early morning, the sun directly flaunts which way is east. The sun always rises eastward. In the evenings, the sun leads us west, for the sun always sets westward. During the day, with no previous references, it may be difficult to know if the sun is in fact south, southeast, or southwest. However, because we know the Earth causes the sun to drift from east to west, shadows cast by objects will do the exact opposite. Marking a shadow at any moment in time, and then marking the same point of the shadow several minutes later, will draw you a west-east line.
When the sun sets and the night is upon us, we can still find the way. We look to the stars. Most stars will mimic the sun across the sky as they rise eastward, drift across the south, and set westward. Drawing one's attention north, we see a different phenomenon. Stars in the northern region simply follow a circular path. None ever set below the horizon. This area of the sky is called the circumpolar region, for all stars in this region circle the pole. The pole is the center point of all rotation, which is located above the Earth's north pole. Being able to find this pole in the sky will indicate which way is north. A very popular star pattern appears in the circumpolar region, the Big Dipper. It's made up of 7 bright stars that form a large spoon or ladle. Stars 6 and 7 of the Big Dipper are often called the pointer stars because they can be used to point out the star Polaris. Polaris is a very convenient star that rests near the pole of the sky. Polaris will not rise or fall, or even appear to move like all the other stars. Instead, it remains in place, all night, every night, leading us north.
Historical records confirm the ancients' understanding of directionality. Ancient Maya cities had buildings and roads precisely aligned with compass directions. Similar precision was seen in Egyptian and Babylonian structures. The pyramids of Giza aligned with certain stars in the sky. The writings about the Hanging Gardens of Babylon state it was properly aligned to the south to receive as much sunlight as possible. The Chinese also oriented buildings, tombs, and even furniture to positions they felt would harmonize with nature.
As our ancestors continued to observe the sky, they started identifying the pattern of the sun and stars in relation to the weather conditions they experienced. Seasons were recognized, and measurements began to predict their arrival.
We've learned that the sun and stars rise in the east and set in the west because of the Earth's rotation. In addition to this rotation, the Earth is also orbiting around the sun. The time it takes Earth to orbit once around the sun is defined as a year. Our ancestors knew this took 365 days from their observations of the night sky.
At the beginning of the year, the January night sky looks like this. Orion the hunter, with his dogs, Canis Major and Canis Minor, govern the sky. As Earth orbits around the sun, we advance through the year. Two months later, in March, Orion and his dogs are now seen closer to the western horizon. Now dominating the mid-sky is Leo the lion and Hydra the water snake. Two months following this, the Otis, the herdsman, shepherds over the land as Leo and Hydra descend. Orion and his dogs are no longer present. As the year continues with Earth's orbit, the constellations that reign the sky slowly shift. After one complete orbit around the sun, a year is complete, and we again see the familiar constellations of Orion, and the entire cycle begins again.
Our ancestors charted the night sky, every night, at the same time. They noticed the stars always shifting westward from the previous night. Why would that be? Earth orbits the sun in roughly 365 days. There are 360 degrees in a full circle. This means Earth orbits around 1 degree each day. Thus, the stars will appear 1 degree further west because of Earth's new location each night. With this understanding, it's quite easy to see how the stars can be used as a calendar to measure the year. Simply look at the position of certain constellations. In December, Orion is south at midnight. In January, Orion has slipped to the south-southwest and Leo is present in the east. February almost sets Orion in the west and Leo rises to power in the south-southeast. March brings the Lion to full command over the southern sky. As we enter April, the Lion tires and begins his recession to the southwest sky. In May, Leo is nearly gone in the west, but Scorpius the Scorpion crawls out of the horizon in the south-southeast. The Scorpion comes to full dominance over the south in June. July announces the arrival of the flying horse in the east, Pegasus. Pegasus chases away the Scorpion completely in August and now dominates over the southeast sky. September showcases Pegasus directly overhead. Pegasus begins its descent into the western sky in October as Orion rises into the east. Orion in the southeast and Pegasus in the west exchange final words in November, before December comes again and Orion takes his place back over the sky.
Where the constellations are a great calendar at night, our ancestors also found ways to tell the time of year during the day. Each day, the sun arcs across the southern sky. At noon, one can measure the height of the sun above the horizon to determine the time of year. In January, the 12 o'clock sun appears here. As the year continues into February, the sun is recorded here. March, it's higher. Each day, the sun at noon gradually increases in height until it reaches its maximum height in June. After June, the noontime sun will begin to descend. Day after day, lower and lower, until its lowest point is reached in December, at which point it starts to elevate and the cycle begins all over. The reason for this rise and fall is the tilt of the Earth as it orbits the sun.
The Earth does not spin on its axis perpendicular with the Sun. Instead, it is offset by 23½ degrees. The noontime sun is at its maximum height in June, because the Earth has leaned us towards the Sun, and thus it will appear higher. As the Earth orbits around the Sun, the tilt remains constant. When the Earth reaches the other side of the Sun, in December, the tilt leans us away from the Sun and thus appears lower.
The tilt of the Earth causes the sun to take slightly different paths across the sky. Lower paths through winter months, higher in summer. A side effect of these different paths are the changes in rising and setting points. Due to the rotation of the Earth, we know the sun always rises to the east side of the sky. In mid-January, the sun rises here. 1 month later, we observe the sun rising here. In March, the sun appears to rise east. As the year continues, the sun rises further northward, reaching its maximum northern point in June. At this point, the sunrise location drifts southward. In September, the sun rises east. It continues to drift southward until it reaches its most southern position in December. Then it drifts back northward and the pattern repeats for the next year.
Our ancestors knew the importance of measuring the year and erected entire structures and monuments to measure it. The Fajada Butte in New Mexico has a dagger-shaped hole in its southern exposed wall. Every day, the noontime sun shines through this hole, casting an image onto its inner wall. On this inner wall are two petroglyphs. The position of the light images in relation to the petroglyphs determines the time of year. Stonehenge, Wiltshire, United Kingdom. This famous rock structure was constructed to help measure the rising and setting sun. As one stood in the center, they simply observed which stones the sun appeared through, specifying the time of year. The Mayan city of Chichen Itza also displayed knowledge of the year. Its most popular monument, the Temple of Kukulkan, had 365 steps, one for each day of the year. Also, on the 2 days of the year the sun sets directly west, a shadow falls on the pyramid in the shape of a serpent. This shadowy snake descends the steps to eventually join a stone serpent head at the base of the Great Staircase.
Understanding how the Earth and Sun interact with each other has given us the means to use the sky as a compass and a calendar. With a little more insight, we can also use the sky as a clock.
Ultimately, the time of day is based on one single factor: the location of the sun. The principle is simple. Local noon is defined as the moment the sun is directly south in the sky. The imaginary line that marks this position is called the median. The time consumed between noon and noon the following day was divided into 24 parts, called hours. Measuring time is simply measuring how far the sun is from the median line.
Starting at 12 noon, when the Earth rotates 15 degrees, the sun will have moved 1 hour from the median, making it 1 hour post-meridian, or 1 p.m. When the Earth rotates its next 15 degrees, the sun will be 2 hours from the median, 2 hours post-meridian, 2 p.m. As the Earth rotates, the sun travels further and further from the median. 6 hours post-meridian, the sun is sinking below the horizon. Since the Earth rotates at a constant rate, modern clocks and watches are able to keep track of exactly where the sun is. At 12 o'clock midnight, the sun is directly behind the Earth on our anti-meridian. At 6 a.m., the sun appears rising in the eastern sky. Halfway between sunrise and noon is 9 a.m., 9 hours past anti-meridian. Finally, the sun returns to 12 noon, and the entire process begins again.
Time is simply the position measurement of the sun in relation to a median line. Familiarizing yourself with how much the sun moves in 1 hour's time will aid you in measuring time. A great tool to use is your own hand. Holding your arms stretched out in front of you allows your hand to give you general measurements in the sky. With practice, you become as accurate as ancient sundials were.
The ancient Egyptians showed great innovation when it came to measuring time. Obelisks were built as early as 3500 BC. Their moving shadows formed a kind of sundial, enabling citizens to partition the day into 2 parts by indicating noon. Markers added around the base of the monument would indicate further time subdivisions. Smaller versions were also produced for measuring work hours. This sundial from Egypt's Valley of the Kings dates back to 1500 BC.
Where you may find time fairly easy to measure during the day.
What can we do at night? We look to the moon. The moon isn't always in the evening sky, but when it is, it can be used to determine the location of the sun, and thus, the time. The moon can be seen in many different shapes. These are called the moon's phases. These phases are caused by the sun's light and the moon's orbit around the Earth.
The moon is lit up by the sun. This creates a bright day side and a dark night side on the moon. As the moon orbits around the Earth, the amount of day side we see will change. If the moon were here, the entire day side of the moon is directed towards Earth. To us, the moon looks completely lit. This is the full moon. A couple of days later, the moon is here. From Earth's point of view, most of the moon's day side is visible, but there is a small portion of its night side showing to us. This creates an oddly shaped moon that we call the gibbous moon. Time passes, and the moon moves around the Earth to here. From this location, we have a very small glimpse of the day side of the moon, the crescent moon. Lastly, the moon may position itself in the same direction as the sun. This causes the entire daytime of the moon to be on the far side and thus not visible to us. This invisible moon is called the new moon.
Beginning with the new moon is in the same direction as the sun in the sky, and thus the far side is lit up. So, if the sun is at noon, directly south, the moon must also be at noon, directly south. The phase following new is crescent. Being a few days after new, the moon has orbited about 45 degrees around the Earth, putting the sun and moon 45 degrees apart in the sky. Using the moon to determine the time, the moon is at 9 a.m., while the sun is at 12 noon. Let's pretend the sun wasn't there. Could we use the moon to tell where the sun should be? First, look at which side of the moon is lit. The lit side indicates which direction to look for the sun. Because this crescent moon is lit on the west side, it's telling us that the sun is west of the moon. Second, remember how the moon became a crescent, by orbiting 45 degrees. We learned that every 15 degrees in the sky is 1 hour. Having moved 45 degrees from the sun means the moon is 3 hours away from the sun. A moon at 9 a.m., move west 3 hours, puts us at noon. And where was the sun? Noon. With a quarter moon, the moon has orbited 90 degrees around the Earth, a quarter orbit. 90 degrees equates to 6 hours of time in the sky. If you see a quarter moon, lit on the east, and in this position, where is the sun? The moon is at 3 p.m. Move east 6 hours, the sun is at 9 a.m. Gibbous moons are 135 degrees from the sun, or 9 hours. Seeing a gibbous moon lit on the west, directly south, where is the sun? Moon at 12 noon, go west 9 hours, the sun is at 9 p.m. Full moons are the easiest to tell time with, for the sun must be opposite the moon. If you see a full moon at the 3 p.m. position, you know the sun must be at 3 a.m. Keep in mind that there are different degrees to each moon phase, and the sun takes many paths depending on the time of year. With more knowledge and practice, you can tell time with the best of precision.
North, south, east, and west. Hours, days, months, and years. Our ancestors relied on the sky to convey it all. Little did they know, their methods and techniques would still work to this day. Their history may be buried, their monuments may crumble, but their knowledge of direction and time will forever live on in our compass, calendar, and clocks.